In this video, we're going to talk about the basics of what's called an electrochemical cell. So coming back up here, this is the drawing here that I'm going to be referencing mostly today. So coming back up here, an electrochemical cell is a cell for generating electrical energy from a spontaneous, and remember a lot of times instead of spontaneous, we use that term thermodynamically favorable redox reaction. Okay, whenever the reaction is a thermodynamically favorable reaction, the electrochemical cell is called a voltaic, really important, voltaic or galvanic cell. Same thing, just two different words for it. The other type of cell, which we're going to talk about later on in this unit, is called an electrolytic cell, and that is when it is not thermodynamically favorable. Okay. So, for right now, all that we're going to be dealing with are voltaic or galvanic cells. And in a voltaic or galvanic cell, there's a lot of stuff going on here. So, first of all, let's talk about the reactions here on the bottom. So, we have a piece of zinc metal, okay? And that piece of zinc metal is in a solution of zinc nitrate. Okay, and that's on, the side doesn't matter, but in this case it's on the left-hand side. On the right-hand side, we have a piece of copper metal, and it is in a solution of copper 2 nitrate. Okay, now those two solutions and pieces of metal, the pieces of metal are called electrodes. So this is the copper electrode, and this is the zinc electrode. So the pieces of metal are called the electrodes. Now you'll notice here that what's happening is that the zinc is that the electrons, notice right here you see the electrons are flowing through this wire. There's a switch here, and when that switch is closed, the electrons can flow. And those electrons flow through here. This is called a voltmeter, and that's measuring basically the electricity that's flowing through there. So in this case, there's 1.10 volts of electricity flowing through there, and those electrons are flowing to here. So how do we know that those electrons are flowing from the zinc side to the copper side? So first of all, well, what's happening on the zinc side? If the electrons are leaving the zinc side and flowing to the copper side, then that means that zinc is being oxidized. Zinc is losing electrons, right? The electrons are leaving the zinc side and they're coming to the copper side. So zinc is losing electrons, and losing electrons is oxidation. And the copper side is gaining those electrons. And we know that gaining electrons is a reduction process. So that means that the zinc is being oxidized and copper is being reduced. Okay, and we can see that in these chemical equations here. We can see zinc is losing electrons and copper is gaining those electrons. Okay, one of the ways that we know that's going to happen, if it's a zinc copper voltaic cell, is we can come back up here and we can see, okay, where's copper on here? Okay, here's copper right here. Okay, copper 2 plus gaining 2 electrons has a cell potential of 30.34 volts. And then we come all the way down here to zinc. Zinc is right here. Zinc has a cell potential of negative 0.76 volts. Which of those two is more easily reduced? Well, remember in our other video, the farther up this list it goes, the more easily reduced it is. So if you have zinc and copper, that means that this one, the copper, is more easily reduced than zinc, which means the copper is the one that's gonna be reduced and zinc is going to be oxidized. Okay, so there's lots of different ways we're going to be able to figure out how do we know which way the electrons flow, but that's one of the ways. We'll talk about others as we do more examples. So the side where oxidation is occurring is called the anode. Okay, now notice that oxidation and anode both start with a vowel. That's how I remember that. Okay, oxidation is, the anode is where oxidation occurs always. Whether it's a voltaic or galvanic cell or an electrolytic cell, the anode is where oxidation occurs. And the cathode is where the reduction occurs. Okay, so reduction, a consonant, cathode, a consonant. So anode oxidation, cathode reduction. Both start with vowels, both start with consonants. So as those electrons flow, what's happening here? Okay, this piece of zinc metal, this zinc electrode, the zinc anode, is going from zinc solid. Okay, this is the solid zinc turning into zinc ions. So you'll see that right here is those zinc ions. So what do you think is happening to the mass of that zinc electrode as that reaction occurs? Its mass is slowly going down. The piece of the metal, the mass of that piece of metal is slowly going down. What's happening to the mass of the solution? Is certainly it is going up because the zinc metal is now turning into zinc ions that are now in that solution. Okay, on the cathode side over here, what's happening on this side is the copper ions that are in the solution basically are growing. They're going to start growing. It's called electroplating or just plating. They're going to start plating onto that piece of metal. And basically it's going to look like the copper is starting to grow on the other pieces of copper that are there. Okay? And so these copper ions are turning into solid copper and creating again an electrode that is now growing in its mass. So the mass of the cathode is increasing. So the mass here is going up. The mass of this one here is going down. And that always happens. On the oxidation side, on the anode side, the mass of that electrode always goes down. The mass of the solution goes up. And on the cathode side over here, the electrode, that cathode, the mass of it goes up, and the mass of the solution actually goes down because, again, those copper ions are precipitating, creating solid copper. Now, the issue with this, and the reason that sometimes these don't work, is because as that reaction starts to happen, as the electrons start to flow, you start to get an increase in zinc ions, and so you get an imbalance in the charges. So what you have to use is you have to use something in the middle called a salt bridge. Okay, and the job of the salt bridge is to maintain the electrical neutrality of both solutions. Okay, well, what the heck does that mean? Maintain the electrical neutrality. Here it is right here. A salt bridge maintains the electrical neutrality of both solutions. Okay, how does it do it? First of all, a salt bridge has to be made of some type of soluble ionic compound, such as sodium nitrate. Okay, and what happens is the NO3, or the negatively charged ions, some might call them the anions, and these, the Na pluses, the cations, right? That because over here on our left-hand side, over here, we're starting to get an increase in positive charges. In order to maintain the electrical neutrality of the solution, the nitrates have to flow into here. Okay, and what that does is, again, with that increase in positive charges, those negative charges come in to keep that solution electrically neutral. And that will still allow these electrons to keep flowing. Okay, so notice that anions in the salt bridge flow to the anode. Oh, maybe that's why they call it an anode, because anions flow to the anode. And big surprise, over here on the right-hand side, where the cations flow to the cathode. Okay, the only thing that travels in the salt bridge are the cations and the anions. And the cations always go to the cathode. The anions always go to the anode. Now, why? We already talked about NO3 minus. Why does that anion go there? Because you're starting to increase that positive charge. You've got to keep those solutions electrically neutral in order for this reaction, for these electrons to continue to flow. So same thing over here. Why do we need these cations to flow into here? Is because we're losing positive charges. And so now we're going to start to get a buildup of these NO3 minuses. And again, to maintain the electrical neutrality of that solution, we need more positive ions to flow into here, because the copper ions are turning into copper metal and thereby reducing the positive charges in that solution. Okay, so notice down here it tells you the movement of cations. And again, it's not always to the right and the anions to the left. It depends which side is the anode and which side is the cathode. Does the anode have to be on the left? Of course not. Does the cathode have to be on the right? Of course not. Okay, but in this case, the cations are flowing to the right because the cathode is on the right-hand side. And the anions are flowing to the left because the anode is on the left-hand side. Okay, and so there's lots of different things going on here. Lots of different things. So first of all, remember again, let me just summarize a few things, that the electrons do not travel through the salt bridge ever. Okay, remember electrons, the one thing they say in chemistry is electrons can't swim. Okay, electrons are not going to flow through the water, through the salt bridge. Okay, electrons must flow through the wire from one side to the other. Okay, electrons, as you can see, flow from the anode to the cathode every single time. Okay, whichever side is losing electrons, that's the side the electrons are leaving. Whatever side is gaining the electrons, that's the side to where the electrons are flowing to. Okay, and remember, anode oxidation, cathode reduction. And remember that here in the salt bridge that the anions flow to the anode, the anions flow to the anode side, again to maintain the electrical neutrality of the solution. Because of the increase in the zinc 2+ ions, as the mass of this electrode goes down, you need negative charges to balance out that increase in the zinc 2+ ions. Okay? And then on the right-hand side, the cations, the positively charged ions, flow to the cathode because the decrease in the copper 2+ concentration causes an imbalance in the charges, and so we need more positive charges. And if you'll notice, for every one zinc that flows in, because it has a +2 charge, you're going to need 2 nitrates. Okay, and yes, they've asked questions about that before. Okay, notice that for every 1 copper you lose that has a +2 charge, you're going to need 2 sodiums to balance that out. Okay, you've got to balance out the charges completely. So for every one of these zincs that comes in here, you need 2 nitrates to balance that. And then for every 1 copper you lose here on the other side, you're going to need 2 of those sodiums to balance that out. Okay? So in the next video, we're going to get some more detail about this. How do we know what that number is? What are some of the ways that they try to trick you, or they make you try to figure out which side is the anode and which side is the cathode? Because once you know that, once you know which side is the anode and which side is the cathode, then everything else just kind of falls into place. Which way the ions in the salt bridge go, which way the electrons go, what this number is going to be here, you know, the mass of which electrode goes down, the mass of which electrode goes up. There's lots of things you can figure out immediately once you know which side is the anode and which side is the cathode.